Hello everyone. In the previous video, we had seen the definition of a random variable from a pure math perspective, from a probability theory perspective. Now it's time to understand it in a more clear way by using an example. So I have a visual representation of a random variable. Let's say we have a random variable x. So as we know, x is mapped from a sample space omega to the set of real numbers, and x is a measurable function. It's a measurable function where it maps from measurable space omega and f to the real sample space and the Borel sigma algebra, as we had discussed in the previous video. Now we have a visual representation of it in front of us, which is this. So we have a sample space omega, which is denoted by this circle, and we have a function x, a measurable function x, such that, let's say, a set of elements a in the sample space omega, when mapped from using the measurable function x, points to some Borel set in the real field. And any Borel set, let's say b, if you take a pre-image of it and form a set in the sample space omega like this, so this set x inverse of b would be present in the sigma algebra for f, sigma algebra for omega, which is denoted by f. Now let's see a real world example of how this works. So this is an example of how a random variable works. So let's say I'm designing a coin tossing experiment. So as we know, there can be only two outcomes of a coin toss. You can either land heads or the coin would land on tails. So the sample space for a single coin toss would be formed by this, heads and tails. And let's define a random variable such that if I toss a coin and it lands on tails, then the value of random variable would be taken up as 0, and if I toss a coin and it lands on heads, the random variable x will take a value of 1. Okay, so we have designed a random variable like this. So let's start by first forming a probability space, and also let's make the coin unfair. So let's say the probability of getting a heads is 0.6, and let's say the probability of getting tails is 0.4. So it's an unfair coin tossing experiment. Now let's form a probability space for it. Now let's assume that for the sample space omega, it has two elements, heads and tails, and obviously this empty space would be denoted by the null set phi. So this is our sample space omega. Now let's form a sigma algebra. So let's suppose I'm using a sigma algebra f. So f is a sigma algebra on omega, and I'm defining f as a power set of omega. That is, it would contain all the possible subsets of the sample space omega. So f would be phi heads, tails, and omega itself, or you can also denote it as this, but to make it short I'm denoting this as omega. So this forms a sigma algebra on omega, and we can very well verify it. Since it's a power set, it will form a valid sigma algebra, and it is non-empty, it is closed under complement, and it is closed under countable union. Hence f is a sigma algebra on omega. Now we form a probability space like this. So is this a valid probability space? Let's check. So f is a valid sigma algebra on omega. Yes, it is. Now let's see if this probability measure also complies with its rules. So as we have seen from the previous video, probability measure is just a measure which has this condition as an extra. So P of omega should be 1. This is an extra condition. The rest conditions of a measure would also be followed by the probability measure, which are that the measure of phi would be 0 and the measure of countable union of disjoint sets would be summation of the measures of individual such disjoint sets. And obviously it's monotone in nature, so P of any set present would be greater than or equal to 0. Let's see if it verifies this, let's see it complies with these conditions or not. So here we know that the probability of getting a heads is 0.6 and probability of getting a tails is 0.4, which means that P of H is 0.6 and P of tails is 0.4. So since these two sets are disjoint, as their intersection forms the null set, so we know that H and T, these two sets are disjoint sets. They are mutually exclusive events. So if you toss a coin, it can either be heads or it can be a tails. It cannot be both at the same time. They are mutually exclusive events. So for mutually exclusive events, we check this property. So the probability measure of H union with T, this is nothing but probability measure of omega, and in this case we have defined probability of omega as we know it's trivial that the coin will either land in heads or tails. It's a sure event, so the probability of omega would be 1. That's obvious. So this is 1, and also the probability of heads plus probability of getting a tails is 0.6 plus 0.4, which is also 1. Hence we know, from this we got to know that P of omega is 1, and this is also true as we just saw. You can also verify it for all such disjoint sets, and obviously P of phi is 0 as there is no coin toss which gives out no result. It will either give you heads or tails, hence this is an impossible event. P of phi is 0, so this is also verified. And from we have checked each element of the sigma algebra F, and we know that if you apply the probability measure on each of its elements of F, all of them are greater than 0, hence this is also valid. So in this case the probability measure is also a valid probability measure. Hence we can say that for this sample space omega, F is a sigma algebra on omega and P is a valid probability measure. Hence this n tuple is a probability space. It's a valid probability space. So now that we have established this to be a valid probability space, where this is H, T and phi, and sigma algebra is the power set of omega. Now let's come to our random variable. So we had seen that the random variable will take up the value 0 when the outcome of a coin toss is tails, and this will take up the value of 1 when the outcome of a coin toss is heads. So which means that, let's say I draw my real number line from minus infinity to infinity, and let's say I have a set which contains heads, and I apply my random variable, which is nothing but a measurable function. So x of h would point towards, as you can see, when heads comes up its value is 1, so it will point towards the real number 1. So this is 1. Similarly, x of tails would point towards the real number 0. Okay, now let's see if we can understand if we take any Borel set present in this real number domain, would it have a valid pre-image? Let's see. So we have three cases. In the first case, let's say my Borel set is something like this. 0, 1. I take a Borel set like this. So we know that the value of x cannot be less than 0. So if we take a pre-image of such Borel set here, which means x inverse of, let's say this Borel set is b, small b, where the boundaries of b, b1 and b2, they are both less than 0. So in this case, we will find no such element present in omega which would give this as the outcome. Hence x inverse of b would be phi in this case, the null set. And is null set present in the sigma algebra F? Yes, it is. So this satisfies the condition. Now let's check another set, another Borel set. Let's say we have a Borel set like this. This time for a Borel set small b, let's say b is of the form a and b open intervals, where a and b both strictly lie inside 0 and 1. So both of them strictly lie inside 0 and 1, and the set of all real numbers between the open intervals of a and b is the Borel set. Let's denote it as this b dash. So if we take a pre-image of this b dash, x inverse of b dash would again be phi, because we know that the random variable x can only take the value 0 or 1. Hence, if you take a Borel set which is in between these values, it doesn't point to anything. So this is also the null set phi, and since phi belongs to the sigma algebra F, as we can see here, hence this also satisfies the condition. Similarly, you can take a Borel set here where both the a and b are greater than 1, and you would again find its pre-image to be the null set, and the null set is present in the sigma algebra F. Hence this also satisfies the condition. Sorry about that. Now let's take a Borel set which has one interval here and one interval here. So let's say we have a Borel set, some Borel set capital B, where this is the set of all real numbers between a and b, where a is less than 0 and b is between 0 and 1. So in this case, we know that x takes up the value 0 when tails is present. So this 0 points towards the tails, so it has a pre-image tail, and obviously the other areas inside this set point towards the null set. So if we take the pre-image of such b, so x inverse of such b would be phi union with the set tails, which is tails. And does this set exist in sigma algebra F? Yes, as we can see here, it does exist in the sigma algebra F. So it has a valid pre-image. Similarly, you can take another interval where this is 0, this is 1. We take a Borel set here, a and b, such that a is between 0 and 1 and b is greater than 1. We can see that the pre-image of b in this case would be x inverse of b would be, so we know that x inverse of the set 1 from the real number line, this is heads, and all the rest of the real numbers would point towards the null set. So this would be phi union with heads, which is the set heads, and we know that this set heads does belong to the sigma algebra F, as we can see here. Hence this also satisfies the condition. Now one last example. Let's say we have a Borel set A and B such that A is less than 0 and B is greater than 1. In this case, if you take the pre-image of B, you would find that x inverse of 0 is obviously tails, and x inverse of the set 1 is obviously heads, and all the rest of the real numbers present in this range would be phi. So x inverse of such a Borel set is phi union with heads union with the set tails, which is nothing but omega, and omega does belong to the sigma algebra F, as we can see here. So we can see that if you take any Borel set in the real number line, and given that the random variable we have defined, which is x, so there always exists a pre-image in the domain omega such that that pre-image always exists. This always exists in the sigma algebra F, and obviously B is any such Borel set present in the Borel sigma algebra B of R. Hence, in this case, we have seen that this is a valid probability space and X is a valid real random variable. Hence, in this coin toss experiment, we have seen that the random variable, which is defined like this, that such that it takes the value 0 when tails shows up and it takes the value of 1 when head shows up, this is a valid real random variable. Now, what are the uses of it? Okay, we have defined it using fancy math terms, but this has a very important application in calculating probability, which you will see later. For a basic example, I can give you this. So let's say I want to check the probability of this. So let's say I select a Borel set B, which is 0.5 to 1.5. So B, let's make it capital B. Yeah. So capital B is a Borel set of all real numbers present in this range, closed interval of 0.5 to 1.5. We can see this is B. Now, if we want to calculate the probability of our random variable x lying between the set of lying between this interval 0.5 to 1.5, what is the probability of this occurring? This can be easily calculated using this concept. So the pre-image of B would point towards the set heads, and the probability that x lies between 0.5 to 1.5 is the probability measure of the pre-image of this Borel set. And what does this mean? So we can see that x inverse of B is nothing but heads. So this is probability measure of heads, which is, as we had seen earlier, probability measure of heads, since it's an unfair coin, is 0.6. So this is 0.6. So if someone asks you the probability of x lying between 0.5 to 1.5, where the random variable x is defined as above, we can easily take the pre-image of it in our original sample space omega and then use the probability measure to calculate this probability, and it turns out to be 0.6. So I hope this example makes the application and the definition of random variable clear in your mind. I hope you like this video. Thank you so much for watching this video.